Hey guys, let's talk about vectors. If you have seen Despicable Me, this villain is named Vector, right? If you have a hard time remembering vectors, you might watch this clip here that's listed in the notes because Vector introduces himself and he explains what a vector is in the little clip. That's pretty cute, and who knew Despicable Me had real physics in it? So just as a reminder, scalars have magnitude only. Magnitude, remember, means an amount, quantity. Vectors have magnitude and direction. And so the direction is as important as the amount. We've talked about several vectors so far. We've talked about these down here. We've got displacement, velocity, acceleration. We'll get to forces in the next couple of weeks. But what's important to note about each of those quantities is that all of them have not only an amount, but they also always have a direction. So with displacement, we're saying 30 meters north or positive 30 meters. And that positive and that north is what causes that to be a vector. Okay, so we're going to take this a step further now and start drawing vector diagrams. We draw vector diagrams using arrows to represent the vectors, and there are a couple really important things about the vectors. One is the length of the arrow should show the relative size. So a 5-meter vector should be quite a bit shorter than a 50-meter vector. Okay, so length shows relative size. The second super important thing is that the vector needs to point in the direction that the problem is talking about. So remember, positive is to the right or up, negative is left or down, and then we will also use cardinal directions, which are the map directions. So that's where north, east, south, and west are drawn in 2D. Okay, so if I have 5 meters north, then I need to point that towards the north on my paper. Okay, one important thing to remember is that north is not actually up. It is when you're drawing in 2D, but if you look at your ceiling right now, you're not looking north, right? So try to make a distinction in your head between north and up and be a little bit careful about that. All right, for almost all problems, you're going to have more than one vector involved. And so we call combining vectors adding vectors. It's a little bit of a misleading name because you won't always be actually adding. If the vectors are in the same direction, you'll add them. If they're in opposites, though, you're going to subtract. And if they make a triangle, you're going to do Pythagorean theorem or SOHCAHTOA or something like that. But all of that, no matter what actual math you're doing, is called adding vectors. You're just adding the parts, basically. Okay? And so when you add your vectors, the parts are called components. And components are important because you're going to follow what's called the head to tail rule. Okay? So head to tail rule means that you'll start with the first vector. So like this one, for example, and then at the head of that one, you're going to start the tail of the next. So if I went that way next, then the head and tail need to be together, okay? So those are the components, and then you have something called a resultant vector. Oops, sorry, wrong button. So resultant vector is always going to go from the starting point to the ending point. It's going to point at the end. So that's this blue one right here where I started here at the start and I pointed towards the end there. Okay? So a resultant vector does not follow the head to tail rule. However, as long as you follow the head to tail rule with your components, your resultant will always be in the right direction. So just to kind of reiterate, components are the pieces, okay? They're the sides, like A and B are the components here. The resultant is your result. It would be your shortest distance straight line distance from beginning to end. And again, it will always start at the beginning and it will point towards the end. Okay. Okay, so this page you have at the very back of your notes, it just says a tip for drawing vectors. Important things to remember. Your arrows need to point in the direction the vector is going. The length of the arrow should show relative size. Components are always head to tail. It's a good idea to label the vectors with the magnitude so that you can remember what's what. And then resultant is going to go from beginning towards the end, so it does not follow the head to tail. However, it is also a vector and needs to have an arrowhead on it. A line is not a vector because a line does not show direction. Okay? And then your answer, your final answer, is the picture plus an answer with a direction and a magnitude or a number and a unit. And all four of those things are important, right? The picture is part of the answer, and then the direction, the magnitude, and the unit are all equally important parts. Okay, so knowing that, let's try some examples. So first we have an airplane flying 100 kilometers per hour north with a tailwind of 20 kilometers per hour. So I'm going to start with my north. 100 kilometers per hour. Okay, and then a tailwind is going in the same direction as the plane. You can put it behind the plane or you can put it in front as long as it's head to tail. Notice that mine is significantly shorter to show that 20 is much less than 100. Okay, and then the resultant is basically just from beginning to the end. Okay, so when we draw it in this way, we can see very quickly that the resultant is just going to be adding the two components together. So the purple are the components, the green is the resultant, and we get an answer of 120 kilometers per hour north. Okay, and my resultant, of course, should always reflect the shortest possible straight line distance from beginning to end. Okay, my next one says now my headwind, or my wind is a headwind. So I'm going to start with my 100 again. And then I'm going to draw my headwind. And there are a couple ways you can do that. I'm going to draw it right next to it. Okay. It is also okay to draw it right on top. So you've got your 100 down here and your 20 up here. What will not work is to draw it like this. Okay, so don't do that, and the reason is that it's really difficult visually to see what's happening when you draw it like that. Instead, with either of the other two possibilities, when you draw in your resultant, you start at the beginning, you point towards the end, and it makes it super easy to tell what you're supposed to do, right? So we can tell that the resultant is going to be a subtraction this time. We're going to do 100 minus 20, because that green line is definitely shorter, right? So we have 80 kilometers per hour. And then for my direction, I look at the green one. And as long as I've pointed my green towards the end, it will be pointed in the right direction. Okay, last one here. We have a crosswind now. So I'm going to draw on my 100. Remember, the diagram is part of the answer, so you have to draw the diagram. Okay, 20 kilometers per hour crosswind from the west. So if I'm thinking normal cardinal directions here, west is over here, right? And it's coming from the west. So that means it's going to be going towards the east. Again, my 20 needs to be a lot shorter than my 100 kilometer per hour arrow. And then my resultant is going to go from the beginning and point towards the end. Okay, this is a right triangle. And so since I know my two sides, I know that I'm going to do Pythagorean theorem to solve for this. If it's been a while since you did Pythagorean theorem, the two sides at 90 degrees are the A and B, and the hypotenuse, or the longest angled side, is C. Okay, so I'm going to do 100 squared plus 20 squared equals C squared. And when I do that, I end up with I end up with c squared equals 10,400, but I don't want resultant squared, I want just the resultant, right? So I'm going to take the square root of that, and when I do that, I get an answer of my resultant equals 101.98, I'm rounding that a little bit, or kilometers per hour. And then for direction, sometimes it's hard to tell when you are drawing it at an angle. So a trick you can do is to put a little set of quadrants at the beginning of the resultant and think about where your resultant is between. We see that we're between north and east here, and so we can say 101.98 kilometers per hour northeast.